we're going to do a little bit of work, a little bit of real life work with our knowledge of exponential functions. And we're going to do this one will be on exponential growth, and the second video lecture will be on exponential decay. So what we want to do here is find and evaluate equations of populations that obey the law of uninhibited or continuous growth. So, uninhibited or continuous growth of cells follows this exponential equation or this exponential function. The number of cells at time t is equal to the initial number of cells, which is how many cells you have at time 0, times e raised to the k times t, where k is the growth rate expressed as a decimal. It's the percent written as a decimal. It's also positive because we're growing, so it's a positive number. And t is the time, days, hours, etc. So we're going to use this equation. We're going to evaluate we're going to solve some problems with it. We're going to come up with it in a couple of examples. All right, so our first example here, example 1, a colony of bacteria grows according to the function the number at time t is equal to 100 times e raised to the 0.045 times t, where the n is measured in grams and the t is measured in days. All right, letter A, determine the initial amount of bacteria. Well, we can look at this equation and we can say the initial amount, because we know right up here the number in front of the exponent piece here is the initial amount. So the initial amount is 100. We can also do it algebraically. N at time 0 is equal to 100 times, times e to the 0.045 times 0 power. Of course, 0 times anything is 0, e to the 0, anything to the 0 is 1, and out comes 100 grams. Algebraically, out comes 100 grams as the initial amount algebraically. But again, we can look here at this equation and we know that the coefficient or the constant in front of the e, the exponential term here, is also equal to the initial amount. Okay, letter B, what is the growth rate of the bacteria? Okay, well here is our equation, the function. The growth rate is the exponential part, the exponent part that comes before the t. So the growth rate is 0.045, which is equivalent to 4.5%. So the growth rate, this is the decimal expression of the percent. So in this case, our bacteria is growing at 4.5%. All right, need some more space here. I've copied the function up here so we can refer to it without flipping the page. What is the population after 5 days? Okay, the number of bacteria after 5 days is equal to 100 times e raised to the 0.045, the growth rate, times the time. In this case, it's 5. All right, let's put 5 into the calculator. And I come up with approximately 125.2 grams is the population. Okay, so just using that in my calculator, let me make my 5 a little clearer here. That's a 5 right there. So pop that in your calculator. You should come up with 125.2. Letter D. how long will it take the population to reach 140 grams? Well, this is the size of the population, so we want to solve the equation 140 is equal to 100 times e to the 0.045 times t. We want how long is how, in our case, how many days? I believe we're talking days in this example. Okay, so we got to solve for t. Well, we know how to do that. We have a base of e, so we know the inverse operation is the natural log. We need to get that e piece by itself. Let's divide both sides by 100 first. And I'm going to have e to the 0.045 times t is equal to 1.4. All right. Now I know I have something equals something. I can take the natural log of both sides, and I do that because the natural log is the inverse of the e to the. So it undoes it. And out from here, on the left side, I have 0.045 times t. I got rid of the e base here. And on the right side, I'll leave it as natural log of 1.4 because I want to leave it as its exact answer at this point. I want to go as close, keep it going, and I'll solve it. I'll do the math at the very end. Now I'll divide both sides by 0.045, and I come up with t is equal to the natural log of 1.4 divided by 0.045, which is approximately 7.5 days. Once you put this into your calculator, you should get approximately 7.5 days. So that's how long it'll take this population to reach 145 grams. You can check it, putting 7.5 approximately into here, and you should get 140 when it comes out. Of course, you could also, don't forget, you could also make y1 equal 140, y2 equal 100 times e to the 0.045x in this case, and when they intersect is your answer, and they should intersect where x is approximately 7.5 days. This is the algebraic solution. All right, letter E. What is the doubling time? Let me keep this a little bit low. Okay, I want to look at that. So doubling. Well, I start off with 100. That's my initial amount. So doubling means I'm going to have 200. So the doubling time says I want to know when the function is equal to 200. Okay, I want to solve this. I have 100 initially. Doubling means I want to end up with 200. And you might notice here, we're back to a very similar situation as this. Let's solve this one graphically instead of doing what we did up here. You could copy this algebraically. Let's solve it graphically. Let's let y1 equals 200. Let's let y2 equal 100 times e to the 0.045, and we'll have x in this case. I'll slide my paper over a slight bit here, get my calculator in there. Okay, y equals, I got something in here, let's get it out of there. So y1 is I want 200 to come out, y2 I want 100, e raised to the 0.045, that's the growth rate, 4.5% times x. Now I'm guessing my standard window is not going to work real well here. I'm starting off with an initial value of 100. So I'll bet, let's see, I don't need to worry about the zero, and I don't need to worry about negatives. X is the time in days. Let's go from 0, let's go to 10 days, see what happens. Okay, now I know my minimum, I start off at 100, I'll go from 0, and I want to go to 200. We'll go to 250 so we can see it. And I want to we'll count that by 50s. Okay, so my thinking here is, I know right here that it reaches 140 grams at 7.5 days, so let's go to 10 days. Let's go to 15 days. Okay, let's go to 15 days. I know it takes 140 grams here takes 7.5 days. Let's go to 15, see what happens. And I know that I'm starting at 100. Well, I'll go from 0 to 250. We'll see what happens. So there's my line I want to grow to. Here it comes. I might not have enough. Oh, I just missed it. Let's go back to the window. We need more days. So let's go to 20 days. Looks like it was right around 15 days. Let's go to 20 days. There's my 200 is my amount. Here it comes, increasing, increasing, increasing. So right here is where it hits 200 days. So let's do a calculation of the intersect. Okay, that's y1, the first curve. There's a second curve. Take a guess. It looks like it takes 15.4 days to reach 200. With my graphing calculator, I'll say 15.4 days. So I could have done it algebraically. I chose instead to do letter E graphically. All right. Let's now do what we need to come up with the growth rate before we can make use of the exponential function. Example 2, a colony of bacteria increases according to the law of uninhibited growth, which I have written here. The number of cells at times t, the number of cells at time t is equal to the initial amount times e raised to the growth rate times the time. In this case, n is going to be the number of bacteria. We're going to count bacteria, and t is going to be in hours. All right, letter A. If 10,000 bacteria are present initially, and the number of bacteria doubles in 5 hours, find the function that gives the number of cells. Okay, I have initial amount is 10,000 times E. I don't know the growth rate, but I know at time 5, I double. I go from 10,000 to 20,000, which will be my final amount here. All right, so we can solve this. Again, we could do a y1 equals y2, but I want the value for k that's exact. So let's do this algebraically. Divide both sides by 10,000, and I'm going to have e to the 5k is equal to, I hope it's 2. It is 2. I can now take the natural log of both sides, which will undo the e to the 5k, and I have 5 times k is equal to the natural log of 2. Divide both sides by 5, and my k is equal to exactly the natural log of 2 over 5. Now I can approximate this with a calculator. Let's go ahead and do that. This is approximately, but I want to keep the exact answer, but this is approximately, let's see here, natural log of 2 divided by 5. This is approximately 0.1386, which is equal to a 13.86% growth rate. Remember, this is the decimal, and this is the percent. Let's get my 8 so it looks like an 8, not a 9. 8.6. But I'm going to leave it k just like this. So find the function. N of t is equal to 10,000 times e to the k. Well, in this case, the k is ln of 2 divided by 5 times t. This is the function we're after here. We used this information to come up with the function. Now we can use this function to solve problems. All right, again, I'm using the exact k. I'm not using a decimal approximation up here. Okay, that function is on the paper, so we can make use of it. How many bacteria will there be in 24 hours? Okay, the number of bacteria in 24 hours is equal to 10,000 times e to the ln of 2 divided by 5 times 24. And we're going to get an approximation here. I'll put my calculator out. I haven't done this one yet, so let's see. 10,000 times e raised to the, okay, it's the natural log of 2 divided by 5 times 24. And we're going to have 278,576.2 bacteria. So 278, I'll round to the nearest bacteria, the nearest whole number. 278,576. After 24 hours, we will have gone from 10,000, doubling at a growth rate, with a growth rate of 13.86%. We'll be up to 278,576. Wow. How long is it until there are 500,000 bacteria? So I want to know, when am I going to have 500,000 bacteria? Well, that should be 10,000. Here is my function. I want 500,000 to come out. I start with 10,000 times e to the ln of 2 divided by 5 times t. Tell you what, let's do this one graphically as well. Let's solve for t graphically. So we'll do this one graphically. So we're going to have y1 is equal to 500,000. I need to note that because my window has to make sure I get up to highest 500,000. I need y2 to equal the right side here, 10,000 times e to the ln of 2 divided by 5 times x in this case. Okay, I'm going to slide this up so we can see the calculator at the same time. There's my calculator. Okay, y1 is equal to 500,000. Hope I got that right. y2 is equal to 10,000 times e raised to the, okay, it's the natural log of 2 divided by 5 times x. Okay, window. Let's see here. And I do know that in 24 hours I got to 278. Let's go from 0 to, let's go to 50 hours and see what happens. And I'll count that by 10. So from 0 hours to 50 hours. I'll use my y min as 0. I got to get to 500,000. So I'm going to go to 600,000. And I'll count by 100,000s. And let's see here. So there's my y equals 500,000 line. Here comes my bacteria growing and growing and growing and getting faster and faster. There it intersects. And that intersection point should tell me when it hits 500,000. Second calc, intersection point. Okay, line 1, enter. Line 2, enter. Take a guess. 28.2 days is when it hits 500,000. So graphically, it takes approximately 28.2 days to grow from 10,000 to 500,000 in this case. So there you have it, working with the function for uninhibited growth. In our next video lecture, we'll look at uninhibited decay.